Okay, so welcome back, and thanks for joining tonight. So let's catch us up. It's been a couple weeks. So this here. Okay, so the three main assignments for this class are the project one, which everyone has done, and then project two, which we'll get start working on shortly, and the final. So you're kind of a third of the way assignment wise through the course. So just make a note that nothing's due for a little bit, but you do have the second project, the final both due on October 15th, so in about a month. I did post your grades for the first project, so you should be able to see the only grades you have at this point are project one. So you should be able to see your project one grades, so you can check those on Blackboard. Let me know if you have any questions about that. But the project one is worth up to 35 points, so that's that's the most points you can get for that assignment. That's all we've got grade-wise so far. Okay, and we've kind of gone through, we did this, CAPM, the arbitrage processing theory. That stuff was for the first project and for the first portion of the class. And what we're going to do from now on, or from this point on, is we're going to introduce some other methods in forecasting. So looked at a couple like stock prices and stock models. And so we'll focus now on some time series aspects, some forecasting, both kind of topics in finance because we'll use your similar data. We're going to focus on exponential smoothing and ARIMA models, which are two big types or two popular types of forecasting. And then we'll cover those two things, or at least highlight those two things today. And then also we'll look at some ARMA models and some unit root testing in eViews. And we'll do that, I think, next time. All right. And then these four main key topics will be the basis for your second project and then also for the final. So I think the plan I'd like to do is kind of introduce these two things, exponential smoothing and ARIMA, show you how to do them in a software program that I want you to use, and then I'll kind of highlight what you're going to be doing for project two. Won't get to all of project two today because there's some other material, but we'll get kind of a portion of project two. You're going to use most of the same data, or you're going to use the same stock prices and do some forecasting analysis, the same data that you use for project one. And so you got to do a little data manipulation and some analysis, but most of the data gathering, you've already done that. Okay, so why don't we start um, introducing these topics and just I'm going to introduce exponential smoothing and ARIMA models. So why don't we start that first? Or actually, let's go to lectures. I want to go through some of the PowerPoints for both of those topics. A lot of slides, but I don't want to go through everything, just kind of introduce the ideas, and then there's some additional reading that you can use to reinforce the ideas. But again, these are two very popular forecasting techniques, and if you're doing any kind of statistical or financial forecasting, you're probably going to want to know how to use these two methods. So exponential smoothing. Okay, so there's a nice additional or supplementary textbook for this topic. And if you click on this little link, I think it still works. That'll take you to this forecasting principles and practice textbook. And this chapter, exponential smoothing, is what we're going to cover the first part of today. So I'd encourage you, it's a free online textbook, so it doesn't cost you any additional money. But if you get a chance, like after tonight or before next week, kind of read through the chapter 7. It's a nice little online text. And so we're really going to cover just chapter 7, chapter 8. But there's some other stuff here if you want to look over that. But if you get a chance to read through to reinforce the ideas, chapter 7, and then chapter 8. So we'll start by covering just some of the highlights from chapter 7, just to introduce exponential smoothing. All right. Okay, so what we're going to do with this type of forecasting method is, well, first of all, we're looking at kind of introduce, I think I introduced different types of data in the first chapter, or that was in the first chapter of the text for this course. And so from this point, we're going to start looking at time series. And time series are just some variable or some financial data that changes over time. So like the data you have for your stocks, I'll show you what. Okay, so the data you have, you already did something like this for your project 1. So if you just looked at like your this Pfizer stock price. So here's my Pfizer stock price. Look at this over time. Okay, look at this specific series, 2001 to 2023 June. So that's a time series. So time series analysis is the focus on one time series data set over time and do some analysis on that. So for the next project, you're going to do a bunch of analysis just on your time series for your stocks, also on your time series for the other stocks. So these other variables, use those for project 1, but now we're focusing on time series forecasting, and you're going to try to forecast in different methods what your stocks are going to be and kind of what those implications are. Okay? So just looking at one stock over time is an example of a time series. Okay. So this type of forecasting techniques is very popular. And so what it does is it gives weighted averages to past observations of the data, like what happened previously. That can help you explain what's going to go on in the future. Okay, so each past piece of data gets some weight, and the weights get exponentially smaller as you go back farther. Okay, so basically, you get it's like an average of all the past data pieces, but that average is weighted towards the more recent data. Okay, so the more recent observation, the higher the associated weight, and you can control the weight, the parameter that gives the weight, but the process is the same. You have some weighting average, goes back, you use past observations to predict the forecast, then the more recent observations have more predictive power. Okay, so I'm not going to go through all these slides, but I just kind of want to show you. So here's like a simple exponential smoothing forecast. So this little y hat t plus 1, that's just saying like you're predicting what's happening in one step ahead of the future. So if you're looking at monthly data for stocks, your stock prices went up, you have data through August maybe, and maybe you're trying to predict what happens in September or what happens in October. Okay? So you're trying to predict what happens in the next period, or maybe like a number of periods from now. To predict that, you're going to use the last observation, the observation 2 periods ago, and so on. And so all those past observations of the same exact variable can help you predict what the forecast is, because usually the best predictor, the best forecasting model is some model that uses what happened in the past to make some inferences of the future. This little alpha is how much weight you give to past observations. So like the bigger this is, alpha, that would mean you give more weight to the most recent observation, and then as it goes back farther, it exponentially declines. So each observation gets some weight, but depending on the alpha, more weight's given to the more recent observations, and you can control the alpha, but the process is the same. So each period you go back, that observation 2 times ago or 3 times ago or 100 times ago, it has some predictive power, but the assumption is in this model that the more recent the data, then the better it is at explaining what's going to happen next, which makes sense because, especially with stock price data, if you don't have any new information, the best predictor of next month or tomorrow or whatever is what just happened, because your best guess is often what just happened or what you observed recently. Okay. This is just an example, but this is the alpha or the smoothing parameter. You can control that, and it can go from essentially 0 to 1. It's got to be something, but if it's 0, then the whole model is 0. But if it's closer to 0, then you're putting a little bit less weight on the most recent observation. If it's closer to 1, you're putting more weight on the most recent observation. But you can see, you go back, 1 period ago. Sorry about that. Yes. Okay, so as you go back 1 period and 2 periods ago and 3 periods ago, you can see that smoothing parameter changes. So it's a bigger alpha, and those pieces of data far back in the future don't have a lot of weight. If it's a smaller alpha, you're kind of smoothing it out more. So you control the smoothing parameter, but the smoothing parameter decays over time depending on what you set it at. So the higher the alpha, the more weight you give to what happened recently. The lower the alpha, the less weight. But regardless, we're still smoothing. Sorry. Okay, I think that's been resolved. So let's see. Okay. So next, let me show you how this kind of works graphically or in practice. So here's a little example. Yeah, here we go. So this is the data for some oil production, some time series of oil production, and we have data from 1996 to 2007, right? I think that is right. And you're using this type of method to get a forecast of what happened and then using that to get prediction of the future. Okay? So um, you can see that the closer the alpha is to 1, that the closer the forecast will be to the last observation. So here's the last observation. And if it's like 0.9, okay. All right. So sorry about that. That's the idea. That's control the smoothing parameter, and the higher it is to 1, the more the forecast will be like the last observation, and then the lower it is, the more you smooth it back or make all the observations from the past a more equal weight. So, for example, here's that data, and here are the time periods, right? Time periods. We have 12 pieces of data, and then this is the forecast, all right? And using different alphas, you can see that if you use something that's really close to 1, your forecast will be very similar to what just happened, right? So if the last observation was 495, if your alpha is close to 1, look how close it is. You're basically saying it's similar to that, but a little bit higher. And then if you decrease the alpha, then the smoothing parameter is adjusted, and the average is more indicative of all these observations, not just what happened recently. Okay, now I'm going to introduce a bunch of different types of exponential smoothing, and it's not that important really to know all the equations or how to, um, set them up mathematically because we're going to use a software program for that. But it is important to understand what these different types do. So that first type, simple exponential smoothing, you basically, if you see the difference in just a normal average, if I took the average of this this historical data, it would be like a straight line, like right through there, right? The average of all this stuff. Weighted average, the exponential smoothing takes an average, weights it more recent observation. So that's why you can see that the forecast starts closer to what just happened because you're pushing more weight to this more recent trend of going up here, less so to what happened back in the past, which probably makes sense because it looks like whatever happened from here to 1996 to 2002, that's in the past and things have changed. So you can use this, but this method gives more predictive power to what's happening recently, right? Rather than just a simple average, which takes everything and gives it equal weight. All right. Okay. Another type of exponential smoothing is called Holt's linear trend, and this is going to essentially not just assign a flat line weighted average. It's also going to allow for a linear trend. So if the data has a linear trend of up or down. So I'll show you what I mean here. So there's different types of linear trends, but see how if this data, the black dots and lines, the historical data is going up over time, it's probably not best just to use a simple exponential smoothing because if you just set some level and go straight, that's not accounting for the trend. So if you see a trend or your software program sees a trend, you can use that to get your forecast. So see how like this is an upward trend. So our linear trend forecast would include some piece of this trend, and allow it to keep increasing. So this is going up. So our forecast, depending on it, it's just a linear trend, or another type is exponential. See that one, which kind of grows exponentially, then a damp trend, which kind of decays off. So each of these items would incorporate the trend. Blue one would just say the trend is linear. The red one will say it increases exponentially. Then the green one, the damp trend, would say it increases but damps off over time. So it's kind of hard to see the methods there, but that's how you would deploy these different types of exponential smoothing. Okay. Okay, so there's a number of different methods we'll try, and some are just like a tweak on a previous. So this one has the additive damp trend. There's also a multiplicative damp trend. Really, that's just adjusting the equation. Either you want to see, like, you don't have to know this terminology, but what it means is that here we're adding, just like it says, we're adding the trend, uh, and in this case, we're multiplying the trend. So this is a nonlinear multiplicative model, and the other is an additive model. And it's not highly important that you understand, have to know these equations, but it is understand that you know what these different methods do. And so this would kind of make it, if you do a multiplicative damp trend, um, this would be a little less conservative. And what that means is damping would be less extreme. So additive damp trend would be closer to the linear trend. The multiplicative would be more like kind of more of a flat line or more horizontal. So the more this gets damped, that would be more of a multiplicative trend as opposed to a additive trend. Okay, so again, there's a bunch of parameters that go into estimating these models, and your software, it's called RStudio, is going to do that for you. So this little chart just shows like you want to do, you don't really have to do this with the parameters, but you want to make some kind of chart when you're doing this analysis. And this is like simple exponential smoothing. This is Holt's linear trend. This is exponential smoothing. This is additive damped. This is multiplicative damped. And what the important thing here is you're looking at these different error metrics. This is the root mean squared error. This is the sum of squared errors. This is the mean absolute error. These are things that the higher the error, then the less close your model was to the actual data. The closer it is, the better your model predicted the historical data. So you'd like to choose, in theory, the model or models that have the lowest errors. Sometimes you don't always get the lowest one for each thing, but like this one, RMSE, that would, if you look across the row, the Holtz one had the lowest error. Also for this one, but this one had the lowest error for MAE. So you're gonna kind of look at error measures and determine which model fit the data better. Okay, and I'll show you how to do that with software, but it's not, again, it's not as important to memorize all the equations and to memorize exactly what these error metrics are, but it is important to know what these different forecasting methods do, and how you can use the errors to pick the best method. Okay, so here's a nice little example of it's everything at once. So you got the simple exponential smoothing, you got the Holtz, you got the exponential, and you got the additive damped and the multiplicative damped. You can kind of see the extremes where the exponential assumes that the data increases exponentially. That's going to increase the most. Holtz is the second most um, uh, because it's linear. This is the multiplicative damped. This is the additive damped. And this is just the flat line simple exponential smoothing, which is a weighted average. And you can see that the weight is up here because it gives more weight to what happened recently. Recently, the data went up. Okay, and there's a lot of information here. And I'm going to show you how to use some of this in the analysis and later to do it with your project too. But I would recommend glancing through the chapter and get another read at these things just to kind of reinforce the ideas. But there's one final type of exponential smoothing category, which is seasonal, and that's going to assume that there's some seasonal aspect that you can incorporate that in your forecast. So there's two types. Additive. Holt Winters are the economists or the mathematicians that came up with these models. So Holt Winters are the seasonal models. So last name of the developers were Holt and Winters, so they coined the model. And the model incorporates the things we had before, level of the series, if there's a trend, and also a seasonal aspect, which would mean that if there's things that repeat historically in seasons, which are months or quarters or something like that, you can use that information to make your predictions. Okay, and don't worry about memorizing all these equations, but the reason why it's called additive is because it adds the components together, and this one multiplies them. So it's just either doing a linear forecast or nonlinear. Okay, and if I can show you this part, yeah, so you're looking, what I mean by seasonal data is something like this. So this is International Visitor Nights in Australia, and I actually don't know what the peak season is in Australia, but they do have a peak season. So that's probably, I do know that it does get very cold, so I would assume that when it's nicer, the weather's nicer and it's warmer, they get more tourists. So maybe that's in the summer, maybe that's not. I don't know the climate of Australia. I do know that when it is nicer, more people go to Australia. Okay? So you can see that every year it's warmer, there's more tourists, and every year it's colder, there's less. You can see that repeating where, peak warm season, cold season, peak warm season, cold season. If that's what's happened historically, then why not use that to get your predictions? Because you don't know what's going to happen in the future, but you know probably that there's going to be more tourists in the warmer peak season and less in the winter because that's what's happened for every year you looked at the data, right? And so you can kind of see that if this is the pattern of the peak, go in the off peak, and your forecast should incorporate that if possible, because it's probably going to happen if that's what you've seen in the past data. And the only difference, usually, for why you want to choose additive versus multiplicative, and you don't really have to. You have to look at the data and kind of choose, but you can kind of compare the error metrics, and it'll tell you which one is better. But if the seasonal variation changes, then that tells you that you want to most likely use a multiplicative method. What I mean is like if these fluctuations are increasing in variance, decreasing, you want to use multiplicative. But if these seasonal fluctuations are staying constant, then that's more of an indicator of an additive. So that's really the only difference in practice is if the seasonal fluctuation, variance is constant, you'd probably want to use the additive. if the seasonal variation is increasing, bigger or decreasing, you want to use the multiplicative. And again, you only want to use these methods if your data is seasonal, like something like this. There's no seasonal aspect in this data, so you don't have to worry about the seasonal aspect because there is no seasonal aspect. So the point is you kind of will look at your data, try different methods, see if you see any trends. Do you see an upward trend, a downward trend? Do you see exponential increasing or damping? Or do you see seasonal aspects like this? And if you do, you can use the appropriate method or at least try different methods to get a better forecast. Okay, so that is quick intro of all these different types of exponential smoothing, and I'll show you how to use most of these for your project. And then fun thing is you'll kind of get to try different forecasts. Because when you pick which one you want, you can visualize the forecast and get familiar with different types and how, depending on what your data looks like, you want to choose different methods or wouldn't. But that's the gist there. So I'm going to show you in a software program how to do some of these things. And you don't have to do it tonight or right away, but eventually you'll want to apply some of these methods and use it for your second project. I'll show you that in a second. We went over that pretty quickly because I want to cover the other forecasting method too, which is ARIMA. But there is more in the chapter if you want to just read through that as I went over kind of the highlights. But any questions on what I showed you or explained? So just any questions or confusion about exponential smoothing? Any questions you can post to the chat or unmute your mic if you want to ask a question. Okay, and again, we're going to do some. So now I want to do some analysis with our data. I'll use my data, and then you can replicate it with yours. And then we'll do the other type of forecasting, and that'll get us a good start on the second project. Okay, so all right, so I think I mentioned this in the first meeting, but if you go to software section on Blackboard, if you can see this, we're going to use this type of model in for the next one today, something called RStudio. And there's a different platform, obviously, if you're using Windows or Mac. But I checked these today and should be updated. So when you get a chance, if you haven't done so already, it takes it'll take a few minutes or maybe half an hour or something. But you want to download this software, and you're gonna use it for the second project. So if I click on RStudio, depending on if you want to do it for Windows or not, you can install RStudio for Windows desktop. There's also some installers for Mac. So that should all be there. And what you want to do is install R for Windows or Mac, and then install RStudio because the RStudio platform requires R to run the software. So if you're running a Windows computer, open the Windows one and download it. But you don't have to do it right now, but just in the next coming weeks. And then if you're running a Mac, I'm going to do R for Mac. and follow these instructions to download. Okay, and then after you do that, you want to download the RStudio platform. So R first, Windows or Mac, then RStudio second. All right, and it might take a little bit of time, and it's usually pretty easy to do, and there's usually no complications. The only complication that comes up is if you're using like a work computer, a work computer, and you don't have permission to do updates and software installations. So if you need to get permission or it doesn't allow you to do these things, let me know. But if you're using your own personal computer, you don't have any like access restrictions, or you can um, download and upload things. Shouldn't be any problems, but it's usually pretty easy to install these things, and it's free. It's really nice software, so I think you'll use it again in addition to this class. But I highly recommend this software and this platform for any kind of forecasting or even just statistical analysis in general. So when you get a chance, install R if you haven't done so already. And then after you install R, install RStudio. Okay, because you're going to need that to do the analysis for the second project. Okay, and then let me show you what it looks like. Okay, so it's when you get it up and running, again, don't have to do it right now. It's going to look something like this. So it's more code based. In the console here on the left, you can put in your commands. I'll show you what to put in. Over here, you got your variable definitions, your plots, and then when you upload data, you'll see a little data set up here. But this is it's kind of got these different windows. You'll type in different commands that you want the software to do with your data. It'll do them in a really nice platform. So I'm going to show you some stuff with exponential smoothing with my example data for the stock. Then the hope is that you can replicate it for your project too. Okay. And again, we haven't got to project 2 yet because we're still learning the ideas, but you will need to use this software at some point. And so let me know if you have any issues installing it, if you have any like access restrictions for a work computer or don't have the permissions, then that's something you'll have to work around. But usually it's pretty easy for students to install this. It is a free platform. I think it's a very good software. Okay, so let me know if you have any issues installing this. Okay, so here's the software. I want to show you some exponential smoothing stuff. And let me show you. Okay, if you go down the exponential smoothing section on Blackboard, and you look, here's a bunch of plots that you can look at later. But I want to show you. Yeah, this one. So there's actually two different example or code files. So this one has a bunch of stuff that you can kind of replicate in the chapter. Then this one I think is more set up for your second project. So if you can see where I'm navigating here, exponential smoothing, instructor example. And then this one that says PFE text, that has some commands that we're going to use to fit the different models. Okay. I'm trying to think if I want to use this one or. Yeah, that's the right one. Okay, so sorry again. You open it up on Blackboard down here, see where it says exponential smoothing instructor example, and then pfe.txt. That should open up a separate window with some code or commands that you're gonna have to modify based on your project, but you can kind of cut and paste this to RStudio to do the analysis. All right, and so let me show you first to get your data into R, and I'll kind of walk you through some of the commands. Okay, so what you want, the way you want your data set up for time series is, here's my example of Pfizer. Okay, and you see that it's just the data and nothing else, because this is how you need to have it set up to upload it into R, and then just save it as a separate Excel file, and you can do it that way. So basically what I did here is so we've got, depending on your time period, you have your stock data for one stock. I had Pfizer and Johnson & Johnson, but each of you had a different stock choices that you used for project one. Use the same data, and you would take all the stock data, like just this piece of data here for Pfizer, and copy and paste it into just a separate Excel file, save it, and that's what you're going to upload. So this stuff here is Pfizer. No labels, no title, just the Pfizer closing prices. That's what I want. And that's what I have here. See? Just the closing prices over time, and that's what we got. So this is my Pfizer closing data, closing price data. So here's like the first price, the second price, all the way to the most recent price. And this is the way you want your data set up. And you're going to upload it into RStudio and run a bunch of analysis. All right, so this is data set for this analysis. Okay, and I'm going to show you how to upload it into RStudio. Okay, so you download R, you download RStudio, you open the software, it looks like this, and it's just waiting for you to do something. So you can do File, Import Dataset from Excel, and you can click on Browse, and then find the Excel file that you set up. Just the data, nothing else, no labels or any other data, just the time series. Okay, so I think this is mine, PFE. Oh, I'm gonna open that, and then because you're not working with any labels, you can uncheck the box that says first row is names, and see how it's just got the stock closing prices, the whole time series, and you can hit import right? And you can see that here's all the stock price data. You have the same number of observations that you had for project one. So this might be a little bit, the range might be a little bit different, but you can see that this is, for this example, here's like the oldest stock price, second oldest, and then here's like the most recent. So it's just, when you upload your data, you'll see it up here in this little window. Okay, then once you do that, I have all these. So again, this is for on Blackboard under exponential smoothing. And down here where it says exponential smoothing instructor example, then pfe.txt should open up a window, or you can save this as a separate text file. But it has some of the commands you can use to do some exponential smoothing. So this, I usually have like the command, then like after the hashtag, it describes what it is. So if you cut and paste this require FPP, actually, just since you haven't used this package yet, you need to load it. If you click on packages, install, and you search for, see where, again, let me, on this other side, packages, install. If I look for FPP, there it is. I hit install. It should install the software, the software package. So FPP is the Forecasting Principles and Practice. It's some code that goes along with the textbook that we're going to use. All right, so first thing you got to do is install the package, and then like activate the package, and then start doing the analysis. Okay. If you go back to this, if I cut and paste require FPP into my console on RStudio down here, enter. Right, you might get some, good stuff, but it should work. So that should activate the package. Okay, and then the first thing you want to do before you do any analysis is use this to convert your data set into a time series. And so this code I give you is the code you're going to use, but you got to modify a few things. So like this PFE would be your data name. See how my data set is PFE. Okay, and then this is like time series, and that would be so I recommend when you upload your data set, give it a very simple name. Don't call it like, cars 1425. Call it something. That's why I just call it lowercase PFE. So I'd recommend just like maybe pick the stock symbol, put it lowercase, and use that as your data name. So the more simple your data name, the easier it is to reference it in all these commands. Right, and then this is the start date of your data. So make sure that this is correct for your data set. So I have, for this example, it's 2001 July to 2022 9. So that's obviously not the same time period we're using in our current analysis, but this is the way I set up this example. So I'll just do this, but I'll do this again for our projects, but I would change this to be the first observation of your data, and this to be the last observation. So like 2001 month to 2022 month. So if you're going from 7/2001 to I don't know if it's like 8/2023 or something like that, then this will be the same because frequency is 12. or monthly. Okay, so you have to use the code I'm giving you and modify it slightly to represent your data or your time series. Okay, so this command should convert your data into a time series. Okay, and if it doesn't give you any errors, it probably worked. All right, and then this plot command, just plot the name of your data set that you uploaded or you're going to upload. See, there we go. There's the Pfizer price over time from 2001 to 2022 or whatever. Okay, so that should work when you do the plot command and make sure the name of this in parentheses is the name of your data set. Okay. Now, just to usually, so here's like the little thing. So here's simple exponential smoothing, and I like to put it. Usually, if you take this whole group, see what I'm doing is cutting and pasting this whole group. That should be one thing, as long as there are no hashtags in it. What I'm doing here is setting up one of the graphs for my data that's similar to the what happened in the textbook. So you would change this to your data set, this to your data set name, and this to your data set. Then everything else is the same except I'm going to call this like um, Ford stock or whatever stock you're using. That's just the label. The rest of this, if you cut and paste it and put it into RStudio, hit enter. See what that did is it took my stock data and ran alpha 0.2, 0.6, and RStudio has an optimal command for choose the best alpha that it thinks is the best. Then it kind of gets a little clunky here because there's 4 graphs in the same picture. But black stuff is the data, the colors are the forecasts historically, and then these are the forecasts going forward. Okay, you should see that the closer the alpha is to 1, the closer it should be to what just happened. So that's why I think the optimal is like 0.9 or something like that. So it's very close to what just happened. But then you can see how the average is weighted to be, we're up in this region because we're assuming we're going to be up here for a while because that's what's going on recently. So your weighted average forecast is weighted to what's going on in the most recent observations. Okay, and then part 2 would be to fit linear trend and exponential trend and a damp trend. And again, I'm just showing you some examples of how to do some graphs and exponential smoothing with RStudio. You don't necessarily have to do all this for your project, but if you want to get practicing and just make sure stuff works, I recommend it. But just make sure you're looking through the code and changing the specific things. If you see PFE, that's my data name, so change that to your stock data. Change that to your stock data. Change that to your stock data, and then the only thing else you have to change is label. But the rest of this should work without any changes. So all this stuff should be set up. Make a few changes to fit your data, your label, and then you can cut and paste it. Enter. So see what happened here is here's my historical data. Those are the different alphas of simple exponential smoothing. And here I'm running, it's kind of hard to see because there's so much data, but I'm doing a Holtz linear trend, an exponential trend, and a additive damp trend on one graph together. And the idea for this analysis is to look at all these different types of exponential smoothing and kind of analyze them, pick the one you think is best for your data based on either what you see over time, or the easier thing to do is just to look at the lowest, which ones have the lowest error, and go with that. So let's say that I thought, let's see what I do. Okay, so looking at this data set, linear trend, exponential trend, and temp trend. It's really hard to. So what you would do is, because the fit one is the Holtz linear trend, fit two is the exponential trend, and fit two is the dip trend. You could look at the error measures of all those things and kind of compare which one has the lowest error and then go with that one. If I want to look at fit one, fit two, and fit three, I could do accuracy, fit one. Right, so there's the accuracy. Okay, then I can look at fit two, accuracy, fit two. Okay, so here's the different error terms for that, like the mean error, the root mean squared error, the mean absolute error, the mean percentage error, the mean absolute percentage error, the mean absolute squared error, and I don't know what this one is, but it's not as straightforward. But the idea is that you want to look, see which type, not right now, but when you do your analysis, which ones produce the lowest error over the historical data. That would give you an indication that would be a better predictor going forward because it was a better predictor in the past. So here's accuracy fit three. Okay, so let's just say that compare the errors, and if I want to pick one of these, let's just say I pick, let's see, how about the additive damp trend? So that would be fit three. You can plot that individually and then get the actual forecast. Okay, so it's fit three because I wanted to choose additive damp trend, and I defined fit three the damp trend. Let's see what happens if you look at them all. You pick which one you want, and then I get the one that's just the damp trend. So here's my historical data, and here's my forecast. And then if you type in fit, it actually gives you the forecast. So basically, like, this number is what this data went from up to um, up to September. Yeah, so this data went up to September 2022. So that means that my next forecast for this one, obviously this needs to be updated because our data is more recent, but the next one was October 2022. That's the forecast for October. That's the forecast for November. And these point forecasts are the forecasts that you get from this blue line. So you can do a 2-year, 24-month forecast, and you can see what those numbers are predicted to be based on your analysis. Now, what if I wanted to look at, so there's, or section number 3, looking at all the 5 non-seasonal methods together. So the simple exponential smoothing, linear trend, exponential, additive damped, and multiplicative damped. Sorry. Okay, so I can look at those here. Again, remember when you're going to copy and paste this, use the code, you got to make sure that you change your data name and the start and end dates to be accurate, or else it won't do the proper analysis. Okay, so I fit those, and I can plot them. All right, so kind of hard to see because we have a long data set, but I fit. So what I did here is we used most of the data to run a model, the rest of the data to do like a test model. So see how we ended it in 2021? That means we used this additional data to test. Like you used all this data here from 2001 to 2021 as to set up the model. You test it on your remaining data to see how accurate it is. So using this as our setup data, this is our test. These are the different methods where you get the simple exponential smoothing, volts, exponential, additive damped, and multiplicative damped to indicate the different colors. So you do this if you want for your historical stock time series. Okay, and let's say I look at that and I just want to pick one I think is best. Maybe since my data is kind of increasing a bit at the end, maybe I want to do. Maybe I want to do. Well, I can see it dips down, so maybe I want to do the multiplicative damped. Okay, multiplicative damped would be fit 5. All right, so there's the forecast from Damp's method with the exponential trend. There's that, and here would be the actual forecast. So for 59, 60, up to 64. See how you can kind of that. Okay, then last part, or the last part of the exponential smoothing, is to look at the seasonal aspects, if there is a seasonal aspect. Okay, so I could fit the Holtz-Winters additive. Could fit the Holtz-Winters seasonal. Holtz-Winters, they're all seasonal, but the multiplicative. And I could look at those in a plot and then pick one. All right, so a little clunky here, but I don't know that this type of data is seasonal, but if it was, or I wanted to use these methods, then here would be the additive, the red one, and multiplicative would be the green one. Okay, and if you wanted to get the forecast from that specific one and the number forecast, you could do like See if this works. There we go. So here's the forecast method from the Holtz-Winters additive. So see how it kind of like there's a lot going on here. So it takes, first of all, it applies more weight to what happened recently. Second of all, it gets the trend. Third of all, it adds the seasonal aspect. So kind of increases and decreases depending on the what it thinks it'll do for the season. And this one would be for multiplicative. Okay, so that's the general overview of this thing. We still have one more topic to do, but try to introduce exponential smoothing. Then introduce how you're going to use that for your second project, and then some commands you can kind of play with. But this is how R works. You can open the interface, upload your data set in the right format, install the package, and then you kind of put in commands. You can get different forecasts and errors. And then I like the plot feature, as some of the commands you put in will do the plot feature. Like here's the time series plot. Here's the plot with different alphas. Here's the different Holtz methods. Here's the damp method. All 5 different types. The exponential trend. And here's some of the seasonal stuff where you get the additive and the multiplicative. And then any of these plots you need, you don't have to do this now for your project. You could export it and save it as an image or save it as a PDF, and just put that into your second project as like a figure or a table. Okay, so what I want to do next is look at the other type of forecasting method, which is ARIMA, and then introduce that in this context as well in RStudio and working with your project data. And then next time we'll do a little more stuff and kind of go through more of your project. At this point, I just wanted to introduce exponential smoothing, show you how to get your data into this software, and then show you some stuff of how you can do some exponential smoothing methods and forecasts in RStudio. Okay. So got some more to do, but any questions so far? Okay, so let's do next thing I wanted to cover, which is ARIMA. So if you go to lectures and you open up ARIMA models, okay, and then this one, if you want to read more about this method, is chapter 8 of that same online textbook. Basically, what we're going to cover the highlights of chapter 7, then chapter 8, and use some of that analysis on our stock data and run some forecasts of financial data. Okay. So if you get a chance, you got a free textbook for chapter 7 or for the whole thing, but chapter 7 and chapter 8 would help reinforce these ideas if you want to take a look at those at some point. Okay. So this type of model is going to use past aspects of the data to get forecasts as well. So we're going to look at lag values of the time series, lagged errors, and then also we're going to look at differencing because that can help you stabilize and get better predictions. Okay, so first, just to introduce stationarity. So time series with any trend or seasonality are not stationary, but if you don't have a trend or seasonality, if it's difficult to predict kind of what's going on in the data, then you would say it's stationary. So the goal of using this type of model is to get your data to be stationary and then run the model. Right? And so if you look at some of these time series over time, if you can see this, there's 9 different panels. And the idea is to see that the ones you can kind of visualize what's stationary and what's not. So any trend would not be stationary. Like this has an upward trend. This has a downward trend. This one you can see is kind of seasonal because it fluctuates up and down. Panel D around the same period. E has a downward trend. F has an upward trend. H has a downward trend, and I has an upward trend and a seasonal trend. So really, the only ones I think that have no trend, no seasonality, are B. See how it kind of just fluctuates around 0, and then G, because there's nothing predictive here in the trends or seasonality. Okay, and so often, or if your data is not stationary, what you can do is take the difference, and that's just like the difference of 2 consecutive observations over time, the difference. So if you take the difference and use that in your model instead of the data itself, that can often help stabilize and make it more stationary. Okay. So this so see this YT prime is the difference, and that's just instead of using the time series itself, you use the difference. So the difference between this observation and the last observation is the difference, and you could also use the difference between 2 observations ago and so on. So if you use the differences instead of YT, then that can often give you a more stable model and be more stationary. Okay, and I'll show you how to do that in RStudio in a little bit. You can also do a second difference, which is essentially to difference the differences. This is not usually, I mean, sometimes it's necessary, but it gets, if you're doing too many differences, it's kind of confusing what you're actually looking at. But if you have really unstationary data, you can also difference it again, second difference, which is the difference of the difference. So that's an option. You could also do seasonal differencing. You have seasonal data, which means that your seasonal difference is the difference between this season and last season instead of just the season. So like this would be the difference between this January and last January, or this February and last January, this February and last February, or like this quarter and last quarter. So you can also difference seasons if that's going to help stabilize your data. So here's kind of what we'll do this in practice a little bit this week, but even more next week, and then for your projects, project 2. So if you look at this drug sales for this A10 anti-diabetic, If you look at just the time series, it's got an upward trend, it's seasonal, and the variance is increasing. If you do log transformation, at least stabilize the variance, right? The fluctuations aren't as uh, pronounced. And then if you do a difference, an annual change in the log sales, what that does. So that makes it stable. It took away the trend. It took away the seasonal aspect. It took away the fluctuation of the variance. So this is not the same variable, but if you want to make your data stationary, you do things like take the log, natural log, or difference, or some combination of both, because obviously this is not stationary. This is. So it looks kind of like, just fluctuations around zero. That's an indication that you've made your data a lot more, if not 100% stationary. Okay, so one difference is the first difference. And we'll do this next time in a different software, which is eViews. But we can do, we test for unit roots. And if your data has a unit root, that would indicate that it's not seasonal. So there's unit root tests. And unit roots, if found, would tell you that your data is not stationary, and you would have to do something to make it stationary. Okay? So actually, while I'm here, let me just go back to this. So again, if you go, I don't want to make you download things a week, but the stuff, the final platform we're going to use is called eViews, and the student version is free, and I checked, I updated the link here. We're not going to use this today, so don't worry about it right now, but if you click on your software, eViews Student Lite version, download, the Windows version and a Mac version, and I will show you some of this next week if you want to get a head start here. And download this as well, and then we'll use this for a piece of the second project. So there's one more thing you can download if you have some time, is the eViews. Again, the student version is free. All right. Okay, so we will do some root testing and eViews next week. Okay, so I'm going to introduce the different components of the ARIMA model. So the first is the autoregressive model. And in this model, or in this type of forecasting method, we forecast the variable of interest using a linear combination of past values. That means that what happened in the past is what we're using to make a prediction for our future forecast. Okay, so see here, we're making a prediction based on what happened last period, 2 periods ago, and back into the future. And our autoregressive model is basically a regression of the model on itself going past. So you can make future predictions based on what happened historically in the data. Okay? And the terminology here is like an AR1 would mean that there's autoregressive model of one, meaning you have one use the last minus one, or AR2 is you have the last two, t minus one and t minus two. Oops, sorry. So you can kind of see that you're setting up a model where it's applying coefficients, or using the happened last time or what happened 2 times ago, 3 times ago, whatever you want to do to make predictions or future forecasts. Okay, and then another portion of the ARIMA model is the moving average portion. In this portion, or this version, we're using past error terms to make predictions. So, like when you run a regression, you know that you don't capture the data perfectly, you capture some of it. Whatever you don't explain is the error term. And those error terms in the past can be used to get predictions of the variable going forward. So if we can take those error terms from the past observations that we didn't observe and use that to make predictions, that's what we'd call a moving average model. Okay? So like MA1 is using the last error term, the current error term, and the last one to make predictions. MA2 is using the last term and then the one 2 periods ago. So changing these numbers in the moving average tells you how far you want to go back with the error terms. And then if we incorporate moving averages, ARIMAs, and differencing, that's our ARIMA model. So this big acronym stands for autoregressive integrated moving average. Okay? And you write the whole thing. You don't have to do this, but the whole thing is composed of differencing if possible. So just note that this is like the general model, but it's possible that your data doesn't need to be done with these things. You might not have to difference. You might not have to use an autoregressive portion or a moving average portion. This is the model. So the model is composed of differencing if needed, the autoregressive portion if needed, and then the moving average portion if needed. So you're making forecasts based on differencing, what happened in the past to the variable, and what happened in the past to the error term. Okay, so this equation 8.1 from that textbook is the general form of what you're using for your ARIMA models. Okay, so we usually set it up like this, ARIMA PDQ, where the first part is the order of the autoregressive part. So do you need past values of the data, and if so, how many back? The difference at 1 or 2, or you need moving averages and how many error terms going back to you need. Okay, and the nice thing about this model is there's a nice auto.arima function in R. It's going to tell you the appropriate model to use for your data set. You can run this, use the optimal model, then that saves you all the trouble of having to, plug and chug or try different methods, because it'll tell you, if you run this, what order you will use. So it might tell you like ARIMA 102 or 012 or something, but usually if you run this optimal function, it will tell you what RStudio thinks is your best ARIMA model. Okay, so see how it, I'll show you this, but you run the auto.arima, it'll tell you like, okay, we think you should run an ARIMA 003, which is no autoregressives, no differencing, but 3 past error terms. And you can run the optimal, you can fit it, and here's like doing that in RStudio. So similar to what we did before, you can kind of see the historical data and what the forecast would look like based on which method you choose. A final thing is we might have a seasonal method for ARIMAs, which means that your data, if it's seasonal, you want to do an ARIMA, would have a non-seasonal part, a seasonal part. So this applies the same that you do autoregressions, differencing, and moving averages. The non-seasonal part and the seasonal part, which would be appropriate if you have a seasonal model. So here, sometimes it's hard to tell if it's seasonal, but it looks like that this data is going up and down different seasons. This is the retail trade index, 17 countries in Europe. So this is wholesale and retail trade, repair of motor vehicles. So possibly retail sales go up in the December winter months because it's around the holidays. So that's typically when retail items are sold, when more cars are sold, so on, like end of the year. So if you expect those end of the year sales to go up during that time and decrease the other time, like in the summer, then you'd use that in your seasonal prediction. If you run the ARIMA model for seasonal data, it incorporates the non-seasonal part here and the seasonal part here, and then this little 4 would indicate that it's quarterly data. So 4 means quarterly, 12 means monthly. Okay, so this a lot going on here, but this would mean that your forecast uses the non-seasonal data, has no autoregressive portions, one difference, and 3 moving average going back. For the seasonal part, no autoregressions, 1 seasonal difference, and 1 seasonal moving average term. All right, and then when you set up one of these models and run it in R, it'll tell you, like, or it'll show nicely, like, here's your historical data, here's your prediction, and you can see that this line prediction is incorporating the downward trend that happened recently, also the seasonal aspect. See, it's going to go up in winter holidays and then down in non-holidays. Okay, so if you want to run an ARIMA, it'll use all the aspects of the data, whether it's seasonal, non-seasonal, trends, and so on, to make the best forecast it can. Okay, so just looking at this data, you think it's going down, it's fluctuating around the seasons, and that's exactly what your forecast assumes is going to keep happening, unless you get some new information, and then you could adjust your model. Okay, here's one final example. This is sales of drug sales historically, and here's the log to help stabilize the variance. If you ran ARIMA model, it might give you the optimal model is this. This is a monthly model. Here's the seasonal, here's the non-seasonal part, the seasonal part, and if you look at your forecast, you can see how well it kind of predicts or goes with what happened historically. So you think your data is going up in this in this season and down in this season, it keeps doing that. So look, your forecast assumes you're going to go up when it's been going up and down when it's been going down. It keeps this general upward trend, and kind of even gives you like the aspect that the fluctuations are getting a little bit bigger. So everything you see in the data historically, this model is going to use that to give you a nice, best forecast it can. Okay. All right. So again, this is the second method. So we're learning exponential smoothing, ARIMA. There's 2 chapters I referenced for that online textbook that you can take a look at and kind of reinforce the topics. But we got a rough introduction of these 2 types. Now I'm going to show you this in RStudio. Then eventually I'm going to show you how to do this for your data, for your project, so you can get a nice, familiar with exponential smoothing models. Choose one for your paper. Get familiar with ARIMA models and choose one of those for your paper, and then discuss the implications. Okay, so if you go to Blackboard, ARIMA, which is right here. rima.txt. Yeah. So I'm going to walk you through these, but these are some starting commands you can use. Start doing some differencing, doing some autoregressive models, moving average models, and full ARIMA models to look at your data. Okay, but again, you have to make sure that you change the names of your data and then the appropriate time period and then everyone's going to have frequency equals 12 because I think everyone's working with monthly stock data. Okay, so this one I have a different data set because it's set up for 1985 to 2022. So I'll update this with you for the current project. But, the commands are the same except for the date range. So let me upload a different time series for this analysis, which is Pfizer. So this one, I'm going to upload this one, which has just the data of Pfizer's closing price from 1985 to 2002 in monthly iterations, just like like we've been working with. So again, your data sets, the upload to RStudio is going to look like this, where it just has the closing prices in column A and nothing else. Okay, so I first go back to RStudio, and you don't have to close it. You can just start right doing a different analysis. I'm going to file, import data set from Excel, and browse, and choose the other Excel file I want to use. And what you want to do when you're importing, if you uncheck first name as Rose, that'll give you the format you want, and hit import. Okay, now we have so here's the same thing, but this one goes from it's a bit longer because it goes back to 1985. Yeah, and so if you wanted, you could go back a little bit farther because you don't have to worry about the same date ranges for like those the home price index or the risk-free rate. Just looking at one time series variable, so you're welcome to use all the data you can find on Yahoo Finance. But again, you can use the same data set for project one if you want. Okay, now load the package again. I think it's already loaded, but just okay. And you want to convert your data to a time series. So again, you're going to change this. That's your data set. You're not doing Pfizer. You're doing Ford or whatever you're doing, and make sure the date range is fitting to your data set. That's got to be correct. Let's do this. Put that here. Okay, let me do a first difference, a second difference in a log. You can see how it makes the data more stationary, kind of the aspect of these transformations. Okay, here's first difference. Okay, so see how that makes it way more. This is the original time series, and it's got a downward trend, an upward trend, maybe some seasonal aspects. And if I do just the difference, how it makes it way more stable or stationary. And if I do a second difference, I might do even more. a little bit. And what if I do a difference of a log? Usually you do the log first, then the difference. That actually this is the difference of the second difference of the log. That's going to really make it stationary, I think. See that? Now it's just like noise. It's fluctuating around zero, and there's no predictable patterns at all. So super stationary. Okay, so you can try that with your data and see if you can, if it's not stationary, if you can make it stationary. Okay, you can run a AR1, which is just one past autoregressive term. Okay, so here's the coefficient on the autoregressive portion. You could run a AR2. Okay, so now you get a coefficient for the autoregressive term last period and the autoregressive term 2 periods or 2 months ago. So the first one we're just using last month's stock price to predict the new stock price. In this one, we're using the last 2 stock prices to predict it. Okay, and if you wanted to see which one was a better fit, you can look at the error terms. Okay, and what you're doing with these error comparisons is looking through all the categories and seeing which one has the lower errors across. So like this one's lower, this one's lower. So they're close, but it looks like on average, I actually have to go through it, but I think this one has the most lower errors in comparison to the other one. What you want to do in your project analysis is look at all the fits, the accuracy of the ones you're comparing, and pick the ones that are the best fit for the historical data, which means that they lower error terms and predicted what happened in the past, and that's an indicator of what you want to predict the future. Okay, we can run just moving average models. Moving average 1. There's the coefficient on the last error term. You can run a moving average 2. Okay, so you get some predictive power from the last error and then the one before that. And then you can look at the accuracy of those if you wanted to. This accuracy function compares any fit you specify. Just note that like whatever you define as fit 1 or fit 2 recently is the one that RStudio is going to reference going forward. So if you define a new fit 1, a new fit 2, or whatever you defined most recently is now the new fit 2 or 3 or whatever. Right, there's some error comparisons here. This one looks like clearly the is better or lower error, so that's lower, that's lower, that's lower. See what I mean? Like MA, this one's lower. The RMSE, this one's lower, and across the board, this one's easy to tell that fit 4 is a better fit than fit 3 because historically the data matched the data, the forecast matched the data better, and that's actually, I'm sorry, it has much lower error terms. Okay, so we looked at the concept of differencing autoregressive models and moving averages. Remember that ARIMA incorporates all those aspects into one big model, which is nice because then you can use that to determine if you need difference, a seasonal aspect, a moving average, autoregressive portion, and if you just do .ARIMA function and put your data set in there, data name, it's not Pfizer, it's whatever it is. Okay, so my best ARIMA model is specified as 1, 1, 2, which means 1 regressive term, 1 difference, and 2 moving average terms. All right, and I could fit that. Okay, so you run the optimal specifier, then you fit the model with that specification. So I'm going to do a 1, 1, 2 because that's what the optimal told me to do. And I can plot it. Okay, so here's an ARIMA. Here's the historical data, up to here. And ARIMA 112 incorporates a forecast which consists of what happened in the last observation, one difference, and then what happened the last 2 error terms. It uses these 3 aspects to get our forecast. The forecast here is blue line, and you can always get. It's hard to see what those numbers are, but if I define that as fit 5, I just type in fit 5, enter. Didn't work. We'll come back to that. Okay, then you can where are we at? Okay, so now the last thing is the seasonal part. So if you do AutoArima and don't specify anything else, it might give you a seasonal model. It might not, depending on your data set. But if you do auto.arima, your data set, yeah, so I got a seasonal model, which is 0, 1, 0, 0, 0, 1, and the 12 indicates that it's monthly data. So if that's my best model, I can run that, which is just 1 difference and 1 lagged seasonal error term. Okay, so I can fit that. I can plot it. Okay, so here is an ARIMA 0, 1, 0, 0, 0, 1, where the first part is the non-seasonal aspect. The second part is the seasonal aspect, and the 12 indicates that it's a frequency of 12, which is monthly data. And here's my actual forecast, the line here. Okay, you can compare them, the 2 non-seasonal versus the seasonal ARIMA. You want to do that? It looks pretty close, but maybe I have to go through and check. They're both pretty close. But you want to look for the model that has the better or the lower errors on average to choose your best. Or in this case, you can just go with the auto.arima function because the idea is that it chooses the best model for you, so you could probably just go with that. Okay, and I could 6 hit my forecast. Okay, so I'm going to forecast. Let's do 6 because that was the auto.arima function. Okay, so these this here, the blue line is my forecast, and the forecast would be next month 49, next month 48, and so on. So you can get a clear indication of what your forecasts are. Okay, and the rest of that that's just okay. So this exercise we learned about ARIMA models. Those consist of the let's go back here. The differencing aspect. Differencing would take the difference between consecutive terms, or possibly a second difference. And this one we did a log because that made it more stationary. Okay, here's an ARIMA 112, and remember the ARIMA consists of the aspects we learned here, which are differencing, um, regressive portion, and then the moving average portion. So those three aspects together would set up the ARIMA. You run the auto.arima function. It'll specify what your best model, RStudio thinks your best model is. You can run that model and get a little graph. Okay, there's the historical data, there's the forecast. You can just get a nice little forecast of what your actual forecasts are. Okay. So again, you don't have to do this right now, but I just wanted to kind of set up these two main forecasting techniques, show you how to use or get you started with RStudio, and then show you some things that what you might want to play around with to get familiar with these types for your data that you got for project 1. You don't need to collect any more data. You do need to understand these two forecasting techniques, and maybe read those 2 online chapters if you want to reinforce. Get this software up and running, and then you can play around with it, or if you have any questions for next week, we can do some more there. So next time, okay, next time we're going to do a little bit in the other software, which is eViews, right? So you can try to download that as well if you want. And so we'll do some ARMA models, which is an ARIMA model without the differencing. You can test for unit roots. Those are 2 more things we'll need as aspects for project 2. So we'll learn these 2 topics next time, or whenever we set up the next meeting. And then after that, I'll show you how to apply all these things to your project. And eventually, I'll kind of highlight the material for the final. And the final is already posted, and so is the project if you wanted to jump ahead. But under syllabus plus assignments, you've got the syllabus, project 1, which you already did. Project 2, talk about that next time, and then here's the final. We'll talk about that going forward. But more things to do, and we'll start applying all these topics, techniques, using data and software for project 2. And the final's based on most of this time series stuff. So we got to get through the next 2 topics first. I think that's what I wanted to cover today. Introduce exponential smoothing, introduce ARIMA, show you how to get your data in RStudio and use that software a little bit. So play around with that if you want. Take a look more at these chapters, and I think that's enough for today. But any questions before we wrap it up for the day, for the night, the evening? All right. Okay. Well, if something comes up in your chapters or your data or using the software, any errors with the coding, let me know. Nothing you have to do 100% for next time, but do try to get familiar with these 2 types of forecasting, and maybe familiar with the software, and maybe try some of the coding and see if it works. It's usually kind of fun, but I think that's all I wanted to cover for today. So why don't we close up here? And thank you all for joining. Hope that was helpful, and maybe we'll do our next meeting next Thursday at the same time, but I'll send out an email to the class to follow up. But that's it for today, and thanks for joining, and I'll see you with some of you next week.
Thank you.
Oh, thank you.